The second part of this lecture is about recursive functions in lambda calculus. We will see how to implement the recursive functions in lambda calculus. Let's first start with an expression whose reduction does not terminate. And actually, it's a good exercise to figure out such an expression, which we call omega. And the desired property of this omega is this omega reduced to omega itself. If we find such an expression omega, it means that we can find an expression whose reduction never terminates. And it turns out that we can derive such an expression like this. So if you apply beta reduction here, you make a copy of these two guys and then substitute here and here. So you end up with this one becomes this one, and the second x becomes the argument. So this expression omega reduces to itself, which means that its reduction never terminates. So the presence of such an expression omega in lambda calculus is a strong evidence that perhaps we can implement recursive functions in lambda calculus as well. So let's try to let's see how to implement recursive functions in lambda calculus. We start with recursive function construct. Recursive function construct, which we write as keyword fun, function name f, and argument x, and function body e. So this is a keyword. And this is our notation for writing recursive function f. So of course, inside expression e, you might have many references to the recursive function f itself. But we don't have such construct, recursive function construct, in lambda calculus. So our plan is we start with this recursive function construct and later show why this construct is syntactic sugar in lambda calculus, in the sense that this can be rewritten as a valid expression in lambda calculus. So it's just the syntactic convenience. We don't have this keyword fun or this recursive function construct in lambda calculus, but later we will show how to expand this one into a valid expression in the lambda calculus. In this regard, this recursive function construct is called syntactic sugar, which dissolves away. So here is a working example. We'd like to implement a factorial function on natural numbers, and we assume that with all the constructs that we defined in the first part, we assume that there is equality function which takes two natural numbers and returns either true or false, Church Boolean, depending on the equality. So if these two guys are equal, this equality function would calculate Boolean true. And if these two guys are different natural numbers, then this equality function would return false. So let's assume this equality function. Our goal is to define this factorial function in lambda calculus. So let's write it as a factorial function. Let's first define this function using recursive function construct. So we will implement it. So we would implement it function f n if equality n 0, then this is the case where n is equal to 0. So you return 0 factorial, the 0 factorial which is 1. So you return Church numeral for 1. Otherwise, you return, basically we want to return a factorial function of n minus 1 multiplied with n. So we return something like a multiplication n with recursive function f applied to predecessor of n. So this n minus 1 is expanded to predecessor n, and this multiplication expanded to this function call. So we have defined this factorial function using this recursive function construct. Of course, we don't have this recursive function construct defined as valid expression yet. So later we will see how this factorial function can be written as valid expression in the lambda calculus. And here is how. From this function factorial, which uses this recursive function construct, we derive a new function which we write as capital factorial function, which is a valid expression in lambda calculus. So this is a valid expression, and this is not valid. This is not valid because in lambda calculus we don't even have this keyword fun. And we transform this factorial function into this capital factorial function, which it takes f, and then which it takes n, and then return the same expression here. So let me copy it over here. So if equality n 0, then 1, else multiplication and f predecessor 1 n. So these two guys are identical. So notice that this capital factorial function is a valid expression in lambda calculus because this is a lambda abstraction, this is lambda abstraction, and this body can be expanded into a valid lambda expression. So we started with this factorial function, assuming that this recursive function construct is available. And the first step is we derived this capital factorial function. Now let's investigate this capital factorial function. This capital factorial function has a very interesting property, which is that given a partial implementation of a factorial function, so this argument f is partial implementation of factorial, then it always returns an improved implementation of factorial. That's a very interesting property of this capital factorial function. So for instance, suppose that this argument f is a partial implementation of a factorial, which calculates the factorials correctly for up to, say, natural number 3. So that is f0 is correct, f1 is correct, f2 is correct, f3 is correct. Then what happens is that the resultant function here, it calculates factorials correctly for up to 3 plus 1, 4. So that's the interesting property of this capital factorial function. You provide as an argument a partial implementation of a factorial function, partial approximate implementation of factorial. Then you always get back another improved new implementation of factorial, which is always better. This is always better than this argument. And as a special case, suppose that this function, this argument function f, does not calculate factorials correctly for any natural number, but that's fine. Still, even in that case, this resultant function, this one, calculates factorials correctly or up to 0, because no matter what kind of function we use for this f, this resultant function returns 1 whenever the argument is 0. So this is the correct result for argument 0. So regardless of the actual function that is provided as an argument for f, this resultant function calculates factorials correctly at least up to 0. So let's provide some silly function for argument f, which is lambda n dot omega, lambda n dot omega. So this function is really silly because it takes an argument and the function body never returns. So we learned that this omega expression never returns. Its reduction never terminates. So this is a really useless function. Now what happens if you provide this guy as an argument here for the capital factorial function, and then you get back another function, and this function is an improvement over this one, and it calculates factorials correctly up to 0. So that is so what comes here is it calculates factorial correctly up to 0. So it's a slight improvement. So let's write it this way. So we have this capital flag. Okay, let me quickly rewrite it. Lambda f dot lambda n dot if eq n 0, then 1, else n multiply n with f applied to predecessor of n. So let's start with the silly function lambda n dot omega. Okay, so lambda n dot omega. What happens if we apply this capital fact to this lambda n dot omega? Well, this lambda n dot omega is a silly function that is completely useless, but the resultant function is useful because it calculates factorials correctly up to 0. If the argument is 0, it returns the correct answer. So let's write it as lowercase factorial 0 to indicate that it correctly calculates factorials up to 0. So we can have this equation. Now, let me apply what happens if we apply this capital factorial to this expression, that is factorial 0. So the argument calculates factorials correctly up to 0. So the resultant function now calculates factorials correctly up to 1. So now let me make a copy of this guy over here. So fact lambda n dot omega, so which is factorial applied twice to lambda n dot omega. Now let me apply this capital factorial function one more time to this expression. So that is, we apply capital factorial function 3 times to this lambda n dot omega. Then what happens is, this function, this one, calculates factorials correctly for up to 1. As a result, now we get an improvement, a slight improvement, which calculates factorials correctly for up to 2. So we return this pattern. So if we have factorial n, it would be capital factorial function applied to n plus 1 times to lambda n dot omega. Because every time you apply this capital factorial function, you improve the approximate implementation of a factorial function. So we have this equation. Now let's go to the extreme case. Now suppose that fact is this function fact without this suffix, without this subscript, this function fact is correct implementation of a factorial. And then let's apply this capital fact. So in other words, what happens if we apply this capital fact to this correct implementation of factorial? So remember that this function is already good, correct implementation of factorial. And we applied this capital fact. Then this guy, this capital fact, always returns an improvement. But there's no room for further improvement because this factorial function already calculates factorials correctly. So this is also correct implementation of factorial. That's the key observation. So in this sense, we may equate these two expressions informally. These two guys are not equal. They are syntactically different. But semantically, this one is correct implementation of factorial. So its behavior should be identical to this function f, fact. So now we have this informal equality between this expression and this expression. So to summarize the story so far, we wanted to define a factorial function. So we can imagine that there's something called fun f and blah blah blah. So this is an example of using recursive function construct. Of course, there is no such construct in lambda calculus. So we will see how this expression actually expanded to valid expression. So the first step is we derive this capital factorial function mechanically. So we have this one. And then we analyze this function and learn that it has a very interesting property. It always returns an improvement in the implementation of factorial function. So f is an approximate implementation of factorial. Then this result is always better improvement. So for instance, if argument calculates factorials correctly for up to n, then this one calculates correctly for up to n plus 1. So we have these equations. if you apply this capital factorial function n plus 1 times to this silly lambda abstraction, then this one at least calculates factorials correctly for up to n, as indicated by the subscript n. Now, we further generalize this observation by taking the argument to an extreme case. What happens if we apply this capital fact to an existing correct implementation of factorial? Then there's no room for further improvement. But the result, this one should be also a correct implementation of factorial. So we have informally, we have this equation. Now, we say that this function factorial is a fixed point of this capital factorial function. So we have to first learn the notion of fixed point. A fixed point is if you have a function f, and if you apply the function f to an argument x, and if the result is equal to the argument itself, we say that x is a fixed point of function f. So for instance, suppose that we have fx is 2 minus x. You can calculate a fixed point of this function f as 1, because if you apply 1, you have 2 minus 1, which is equal to 1. So the argument, the return value are equal. So we say that this function f, 1 is a fixed point of this function f. Okay, so that's the notion of a fixed point. And now we only have to calculate fixed point of this function capital factorial. Then we obtain the correct implementation of factorial. So to summarize, in order to implement recursive function factorial, we have to calculate the fixed point of this capital factorial function. Factorial function is a fixed point of capital factorial. Now, how do we calculate this fixed point of capital factorial function? It turns out that in lambda calculus, there is something called fixed point combinator. Fix, which takes a function f and returns it takes a function f and returns a fixed point of this function f. So there's such an expression of fixed point combinator. So we will see the actual expression later. Then, in order to calculate factorial function, you only have to calculate the fixed point of this factorial function. So this f fact is fixed point of factorial. So therefore, if you apply fact to this fixed point, you get back the same expression. This is a bit hard to read, but it's pretty easy to see. It's a fixed point combinator, takes a function f, and returns is a fixed point. So fix f is a fixed point of function f. So if you apply f to fix f, you have fix f, according to the definition of fixed point. So to summarize, in order to define factorial function, first derive this capital factorial function. and then apply this fixed point combinator, and then you obtain this factorial function. Then what is the actual definition of this fixed